helping you with Acorn and RISC-OS computing.
So yeah, I guess I'll start with a little bit about sort of some background, what I know about some of this. So I've been doing sort of stuff to do with things related to Filecore for some time. One of my initial forays into this was back when the RISC PC 3.6 came out, and we had bigger disks but massive LFAUs at the time. And one of the sort of ways around this was to split your disk into smaller sort of partitions, and that was the thing called BDFS, which was sold by Claire's at the time. It basically was a soft loadable thing. You'd shrink the ADFS part of your disk down and put some extra Filecore partitions after it, to means you could have smaller disks as far as Filecore was concerned, which meant you could have a smaller LFAU, and then saving a text file didn't take up 30 kilobytes or something ridiculous. So yeah, but more recently than that, I did some stuff with some Python to read the Filecore map and directories and things like that. And that was actually part of an idea I had, which was, can I resize the SD card that comes with, RISC-OS for a Pi? I did write some scripts and some instruction how to do it. Yeah, you can do it. It's quite fiddly. And you can also just buy system disk for 10 quid or something. But, well, the technical challenge isn't there then doing that one, is it? So it's a bit about what I know. So this sort of talk is basically what I've sort of found out along the way. I can't guarantee to be any sort of expert on this Filecore stuff. So could well be wrong. If they are, let me know. But yeah, hopefully you'll sort of get the idea, if nothing else. All right. Next slide, please, as they say. So what is Filecore? Well, I decided to ask ChatGPT, which gave us this bit of a summary. Yeah, it's kind of it's on the right lines, I guess. ChatGPT's output then went on to some other stuff which is blatantly wrong, but that's about right. So but yeah, it's the module that handles disks basically. Let's go to that. So it's based, as you may be able to guess, on ADFS, and in fact, ADFS was the first kind of user of it. But ADFS itself predates RISC-OS by some years. I think it was first seen, I guess, on the Electron with the +3, which was that big L-shaped thing that you plugged onto the machine, and had a floppy drive on the side. It was also used on the BBC Micro for Winchester, as they're called, hard drives, but not floppy disks until the 1770 upgrade came about, because it needed the double density that chip provided. My notes here says, initially you could get ADFS on the Electron if you're rich, and on the BBC if you're very, very rich, because hard drives at the time were really expensive. The Master 128 and Compact also included ADFS. Gonna get the feeling that the Master Compact was used it more. The Master 128 generally people would use with a 5¼ inch floppy drive, so that was generally DFS, because it would then compatible with the BBC. The Master Compact had the 3.5 inch drive, so same as the Electron. So it was less of an issue that it didn't fit the BBC, because the physical disk wouldn't fit. Then Arthur, obviously the precursor to RISC-OS, had ADFS as well. Okay, but the next thing after the Compact, in that sense, the early Archimedes was after the Master, so they kept ADFS. So just a slight sort of note here. Obviously, initially, most of these users would have been floppy disks. Hard disks were very, very rare and very, very expensive. So in the Electron master era, formats were kind of given the acronyms small, medium, and large. It says there, the 40 tracks, 80 tracks, and 80 track double-sided. There wasn't a 40 track double-sided. There wasn't a configuration that Acorn bothered with. So discs of any sort of rotating disc type things have got heads, tracks, sectors. So, one or two heads in terms of a floppy. You can't have more than two. Each surface is then split into tracks. Sorry, 40 or 80. Each track is split into sectors, and each sector is a number of bytes. You'll see the BBC era ones, the sectors are 256 bytes. I presume that's because that was a page on the 602, so it's a lot easier to work in pages. Because they were smaller, you had more of them, but not as much storage as the Arthur version, which was, I presume, D for double. Can't think of any other particular meaning for it, which had fewer sectors, but they were 1 kilobyte each. Obviously, much more memory, even on a 0.5 megabyte or 1 megabyte Archimedes. So, yeah, having a kilobyte for a sector, not such a big deal. That meant you could have more storage because while sectors were bigger, you had fewer of them, but there were less gaps between them. So overall, you got 800 kilobytes, which was what a D format disk was. And the D format was kind of like the large format, only a bit bigger. So yeah, that was more of the that's what was to do with the floppy drive, floppy disks. The D format had, I think, a bigger directory, so you could store 77 objects rather than 47 of the BBC. And Arthur hard drives, if you had one, which would be pretty rare, would also be basically based on the D format. Yeah, it's like a floppy disk, only a lot bigger, more heads, more tracks, whatever. So yeah, that was sort of up to the Arthur days. So a little bit of history here. I mean, Arthur was late 80s, so that's at least 5 years ago now, right? So then RISC-OS came about and added the E format, which was still 800 kilobytes. Yeah, high density floppies weren't really a thing until the A5000 came out, but it offered quite a few useful advantages over the previous D format. One of which was you didn't have to compact the disks. So anybody who used ADFS on a Beeb, or I guess on Arthur, I didn't really use Arthur, but I definitely had it on a Beeb. You occasionally there'd be enough space on the disk, but you couldn't use it because it was all split up, and you'd have to compact the disk, which would coalesce all the files towards the front. It was extremely fun on the Electron because the compact code would corrupt your disk if you didn't turn off the cursor. So yeah, that was good. They didn't fix it because apparently there was a workaround which was turn the cursor off. Yeah, I think it used screen memory. So yeah, that was not so great. So yeah, compared to the previous the BBC era stuff, you have more elements per directory. There's still 10 characters, and you could add defects after formatting. I believe previously you had to kind of put them in. Adding a defect changed the rest of the addresses, so it's quite hard to add a defect after the event. 77 entries per directory, 10 characters maximum. This kind of 10 character limit sort of became known as a RISC-OS limitation, although technically it wasn't. Other filing systems could have more bigger file names even back then, but everybody used ADFS really, or later on some variant of it. So 10 characters kind of became a bit set in stone, and certain programs, the impression was one would get very upset if you did have more than 10 characters in a file name. Crash, I believe, but memory was short, memory was tight, so you could sort of see they had to pick some limit. So yeah, that was kind of the E format. This is what I'm going to talk about for the rest of the talk. The E format, which is the new, basically called the new map. The high density floppies, the F format, will basically bigger versions of the same thing. I think the high density floppies were a little bit like tiny hard drives more than floppy disks. They had the map was bigger, but we'll get onto that later. So yeah, that was what we're going to talk about now. The E plus format, which we'll get onto later as well, which is the one everyone uses these days, is very similar. It's kind of got different directories because you can have longer file names. So I'll move on. The title of this slide is probably slightly confusing for those who are not in the know. I will get back to why it's called that later. So late in the 1970s, not that old, 1980s, when hard drives are hard drives, as I said. They're loud, they're big, they're expensive, and they were basically made out of what's now known as spinning rust, plates of some sort of metal. I presume it wasn't actually rust, but moved, accessed by heads that moved around, the whole thing span around. Initially, it would have been a low-level SD506 interface. I think the A540 had one of those. You could buy it for 300, 310 or whatever. This was sort of in the era when disks had the info about the disk was printed on it, including the defect list. You couldn't get it any other way. That was, you had to physically type it in. There's no way of interrogating the drive. It was really quite a low-level thing. Basically, the controller could tell the head to move in and out, and, read and write data and stuff, but there was no intelligence. Later, SCSI and IDE were more common, and they did have that sort of facility. But as with anything that's built of a disc-shaped thing, you've got cylinders, you've got heads and sectors, which is the CHS model. But actually, mostly within Filecore, it treats everything as just a big list of blocks, which has got logical block addressing. So the terrible pun with the name of the slide is that Charleston Airport in America has the airport code CHS, and Leeds Airport, as in Leeds Bradford, has got LBA, and Charleston to Leeds. So yeah, it's basically within Filecore, everything just treated as a block number from the start of the disk, and you kind of hide the details of the heads and cylinders and all that sort of stuff. Which makes it slightly easier. So Filecore does have a boot block, which contains a bit of information. Mainly it's the defect list. Again, I guess this kind of goes back more to the time when defects were expected, certainly on hard drives. Like I say, you could buy a hard drive, it would have the defect list printed on it. And it was kind of accepted that, it would grow over time. Eventually, you'd probably bin the drive if it had too many defects on it. I think now if you have a memory card, which is so tiny, can't get in the camera, if it had anything wrong with it, you copy the data off and throw it in the bin because it's cheap to replace. If you're using a hard drive that cost several £100 in 1989 or something, you don't want to bin it because it's got one defect. You can just work around it. Hence the defect list. Less of a useful thing these days, I guess. But again, back to the era when it was started. The same applies to floppy disks. I definitely, as a poor student, had several floppy disks that had defects on them, but I thought, it's all right. I can keep using it, right? Until eventually they did die. But that was money I could spend on beer that I didn't then have to buy another disc with. So priorities. So most of this stuff now is sort of going to continue on this talk is really more to do with hard disks than floppy disks. Floppy disk kind of stuff is more kind of indication of where it's come from and what it was used for. In the it wasn't until probably the mid 90s that I would say most users had a hard drive, and even then quite a few people would have been working on a single floppy system. especially with the high density floppies, you can kind of get away with it. Hard drives are expensive, so yeah, so there is that kind of legacy of having to support that as well. The disk record, it's an interesting thing. It tells you varying things about the disk. One of the things it tells you is the size of the disk, and the number of heads, number of sectors, number of cylinders, and how big each sector is. Some of the information about the map, which we'll get onto later. Part of the reason that you need to store that information in the disk record is kind of what I was saying earlier. You can't rely on reading it from the drive, and this is where BDFS actually used this to its advantage, because the disk record was kind of implied the disk was smaller than it really was. So ADFS would then read the disk record and go, oh, it's this disk actually got 2 gigabytes. I'm trying to remember the right units now. I think it was gigabytes. So the disk might have been 2 gigabytes, but we're only using half a gigabyte for this partition. Yeah, I think that's right. When you go back so long, or the units get so small, I forget what it is. But so yeah, because that wasn't always there, you had to be able to read it. The boot block is always near the start of the disk. It's actually at address C00 hex, which if you've got 512 byte sectors, which is the most common one, it's sector 6. I presume that's going to be the case. That's always going to be track 0, head 0, sector 6. So you can always find it. You can always get the controller to find it. You then read the disk record. Technically, there are 2 disk records. There is one in the map and one in the boot block. The one in the boot block, it's only supposed to give you enough information to find the one in the map, but normally they're the same, because having written the one in the map, you might as well write the same one to the boot block. It's got some odd stuff in there, like, is the disk 40 tracks? It's not being very useful anymore. But again, another sort of nod to its kind of heritage, what it was for. There's also in the boot block a little bit of information that was there for RISC-X, the Unix operating system that Acorn did for the A400 series. They were called something else. They are something or other, but they're basically, Archimedes machines with their own version of Unix on it. So yeah, there was a little bit of information in there which would store a little bit of stuff about RISC-X partitions, where they were. I don't think anybody's going to use that these days. Someone's got a 540 with RISC-X on it, which case, well, fine, it's there. Doesn't really give you much in the way of useful partition information for anything else, but yeah, it's there. Obviously, they had to put it in for RISC-X, so that's in the boot block. It's handily not at the same address as the MBR partition block, so it won't get splattered by that. I think when you format a disk, you normally get a MBR boot block on it, MBR partition table on it. It just says this disk's AD, I think is the partition type. Just so a PC or something else won't grab the disk. Oh, it's totally blank. We'll write a partition table, format it. So yeah, the boot block's there. Basically gives you enough information to find what you need. So the kind of main focus of what I'm going to be going over, I guess, is the map. There is a nice map of Wakefield there. I thought I had to pick Wakefield if I'm going to show a map. And basically, the map describes what's on the disk, much like a map of Wakefield shows you what's in Wakefield. 800 kilobyte floppy disks only had the map in one sector. That was big enough. Obviously, as you go into hard drives, and in fact, the high density floppies, that wasn't really big enough. So it's split into zones, which is basically a sector's worth of map. The map itself is treated as bits, not bytes. So it's basically a big bit stream. And one bit in the map can relate to a given chunk of the disk. So I guess much like a actual map, like this map, an area of the map maps to an area in real world, as it were. And that's kind of the scale of the map, I guess. And it's the bytes per map bit, which is very hard to say, oddly. And that actually is the LFAU value. So that's how much disk is per bit in the map. Obviously, a map's no good if you can't label it. So the labels are stored on the map. So you've got, you're in your binary data, your binary bit stream. You can write the labels. Basically tell you what's there. So you might say this bit is a particular fragment ID. I'll go on to this all later, but this bit is part of this file. This bit is part of this file. This bit's empty. And there's a musical reference there for anybody. Our map in the middle of our disk, but the map is always in the middle of the disk. I am presuming, but not sure I've ever seen this officially documented, that it's there because that means on average you're only going to have to go up to half the disk to get to it. And because it's quite a key thing, you will need every time you need to do anything, you need to go to the map. If you have a physical spinning disk with heads that move, if it's in the middle, maybe you only got to move half. You don't ever have to move up to halfway across the disk. If you put it at the front, right at the beginning, if your head was currently the far end of the disk, you'd have to go all the way back to the start. Less of an issue on hard drives, I guess, but if you have floppy drives with slow head stepping times, probably made a difference. Which is why I'm guessing they put it there, but it's always in the middle. So to find the map, the first you do is find the middle of the disk. So as I was kind of saying earlier, the things you store on the disk need to be identified. Otherwise, you've just got a nice map of there are things here, but I'm going to tell you what they are. And they're stored in what's called fragments. I read a typo on my slides there, never mind. Each fragment's got an ID, which is a reference number for it, and they can be currently up to 21 bits long. Most things on the map kind of work in bits, so you have to kind of remember that. And from an ID, you can find the fragment in the map. And then you know where it's on the disk. So I've got an example there, some pretty coloring. An example, I've gone for 15-bit IDs. There's so many bits on the screen. So this is for ID 1234, which is that binary number. Obviously, it's 15 bits, so it's padded out with zeros. And then these, can't see the mouse, can you? So after the sort of the red portion, there are 4 black zeros. They are really there to say, this object is taking this much space, and there's always a 1 at the end to say, that's the end of this object. So this object 1234 is going to take 20 bits in the map because it's 15 for the ID, 4 for the zeros, and then the final 1 at the end, so that's 20. So on the disk, it's going to take 20 times whatever the LFAU value is. So this kind of getting into sort of the complications, I guess, of where the LFAU comes from and how it all fits together. So the ID length determines the minimum size of the object. So if the minimum thing you can allocate in the map is going to be the number of bits you have for the ID plus the 1 at the end. So if you've got 15-bit IDs, you need 16 bits for your minimum size. So that's 16 times the LFAU, and that's because you always need to have room for the label. So you can't write the label if you got a label or something, and then you can't then refer to something that's smaller than your label because you kind of had to write the label. So that does mean there's a restriction there on the minimum size of thing you can actually have in the map. So if you have a fragment, you have a fragment ID, you will need to find it in the map. I guess you could think about, well, I'll just start at the beginning of the map and trawl through it. But the maps can get quite big. It's quite an intensive thing to do to search, linear search. So we can do better than that. So yeah, find a fragment ID, you need to find it in the map. The first fragment ID you'll need to find will be the one where the root directory lives. I'll come back to that in a bit. So there are the sector size in bits per zone minus the overhead. So it was always multiply 8, of course, because it's bits. So the sector size will tell you how big each zone is, because I think it was sort of earlier, each zone is one sector, and there can be a gap between each zone and the next zone. Like you may not fill the entire sector. Normally it does. I think F format floppies it doesn't. I think most hard drive type things I've seen will have it as it will be the entire thing. So that gives you the number of bits per zone. So if you have a standard 512 byte sector, you get 8 times 512 number of bits minus a bit, because you have the overhead and the header. So that basically then from there you can say that the minimum size of anything in a zone is going to be ID len plus 1. So the length of the ID plus 1 for the termination bit. So in this case you'd have 16 bits. That gives you the maximum number of things you could store in any one zone. And then that then means you can divide the ID you've got by that, and you know where to start. And then that's a zone you can then start looking in for your fragments. They're called fragments because each file may well be stored in more than one fragment. Certainly big files they'll have to be, because they'll be, they need more than one zone's worth of information. So you'll start at that point, start working through that zone. You'll find your fragment, and you'll know how many bytes you're expecting to make your file. So if you're saying I want to open this file, it's 200 megabytes long or something. You can go to the map, you can find the first fragment. You'll then know, well, this fragment actually maps to 64 kilobytes or something. So you go, well, I've still got more to go, and you just keep searching in zones after the one you started at until you've found all your data. If you get to the end of the disk, you wrap around to the start, and hopefully that will find all your data. I imagine if it doesn't, it'll probably crash. But I've not tried that sort of thing. Disk night will have to fix for you. So yeah, that's how you can find your data on the disk from the IDs. But fragments can be shared. So there is a idea that because the minimum fragment size is much bigger than you can have a small file. You can actually share a fragment amongst several files. The kind of common use for this, I think, is that a directory will share a fragment with its immediate children. Kind of quite useful, because not only got like the run file, the boot file, possibly the sprites file, depends how big that is. All those sort of little files that go with an application can actually share the fragments. They don't take up too much disk space. And I believe siblings can share fragments, and my notes here say that they probably share better than my kids share anything with each other, just because they're siblings. Sibling rivalry. But I don't think they fight over the fragments. Maybe they don't insist they have the same number of bits each. He's got 1 bit more than me. That's not fair. But yeah. So initially, this actually sharing thing was done in terms of sectors. It's now slightly different, and because everything's got bigger, you can actually have it's sort of scaled up a bit, so there's actually a share size. But yeah, ultimately, it just says how far into the fragment your file is. If your files are too big, then it won't be shared anyway, so it'll just be normal fragments. There is kind of things happening with if you delete a file that's in a shared fragment, obviously the rest of the fragment has to stay there, so everything has been deleted. Yeah, I guess it's reusable, but yeah, you don't get the space back until everything's been taken out. And there are also a couple of special fragments. One of the kind of things you have to remember, I guess, is that the map has to contain the map because the map's stored on the disk, and the map describes what's on the disk. So you have to kind of say, here is the map within the map. It's a little bit meta, isn't it? Along with the boot block and the root directory, is actually given a special ID of 2. It's treated slightly differently. The map's always in the middle of the disk, so the ID doesn't relate in the same way as all the others as to how far in the disk it is. It's 2, it's the map, it's in the middle. And the defects and the slightly confusing bit of the map off the end of the disk. So I'll go back to, I'll give an ID of 1 on the map, on the new map. Basically, defects are listed in the map, so we just don't try to write to them. But this means you can add to the defects after you've formatted the disk. So the bit of the map off the end of the disk is where the zones you've created. So maybe you've got 5 zones for your disk. Well, no, it'd be 4 because it's always going to be a power 2, I suspect. That probably doesn't map exactly to the exact side of the disk. There's going to be a bit of the map which is off the end. I kind of view it like a bit of map that's shaded out. Can't use this bit. And that's given a fragment ID of 1. I guess a bit like a defect, you can't use it. So yeah, just that it's there. So yeah, they're kind of special fragments handled slightly differently. The other concept is free space. Obviously, you know where files are, but you also need to be able to know where space is if you want to store things. So each zone, which is each page of the map, I guess, it's got a header. It doesn't really contain a lot, but one thing it does contain is an offset to the first, what's called the free space fragment. This is basically a fragment that just says this is free space. Because things can be put, normally when things are put in, they're going to be, going to start at the top and work down, but things get taken out, things get moved about. So it's a list because you could have pointed to the first bit of free space, then some files after that, then there's another bit of free space, and some files after that, and another bit of free space, and so on. So yeah, each entry in the list contains a link to the next one, and it's actually done by the next one is at this many bytes offset from where we are. So that actually includes the one in the header. So the one in the header tells you how far in the zone you have to go to get the first bit of free space. That's how far to go to the next bit of free space, and so on till the end. It's stored as a 16-bit value because the header's 4 bytes, 2 bytes are checksums, and 1 byte's the free space link. I think that gives you up to. It would let you have sectors up to 8K because a zone has to be the same size as a sector. Biggest we have now is 4, so probably not an issue. When you're storing when the free space fragments are stored, they are padded out to be the maximum. Sorry, to be at least the ID length. So that means you can always put something in. Otherwise, you can have a 16-bit offset, but then you could never use that gap for anything for a fragment. So yeah, I think it's kind of a bit of initially the ID lengths was small enough that it wasn't an issue. But now we've had bigger IDs, reason of come to you later. So we've got to kind of allow for that. There are two check bytes in the zone header. One is a check byte of that zone, and one is a check byte that maps all the other zones. So if they all have to add up to something. So if you change one and not the other, you need to make sure the numbers stay consistent, or you get bad free space map error. I think doesn't Filecore gets very upset anyway. But yeah, they're only single bytes, so they're not that great for detecting things, but they're there. And everyone's favorite, the LFAU, the large file allocation unit. It's kind of touched on this a little bit earlier with the old 3.6 era stuff. It determines basically how big things are on the disk. It's the scale of the map. It's the same as the bytes per map bit. So it's the size. It's determined by how big the disk is and how big the map is. Because obviously, if you've got a big map, if you've got a big disk and a small map, each bit on the map is going to be a big bit of the disk. If you've got a smaller disk and a bigger map, each bit on the map takes a proportionally smaller part of the actual disk. So, but it's not quite a simple thing of, well, the disk's bigger, we need a bigger map then, because there are varying limits which come into play, which I spent a lot of time going over when I was trying to write a bit of Python code, which did manage to get to work to format layout a Filecore image effectively on a Linux system. There's quite a lot of factors that come into play. One of which is you need to be able to address all the fragments. So if you have a big map, if it's too big, you can't get to the last fragment because, saying before, you work out how many fragments you get per zone, which basically, and then that with the length of the IDs basically limits how many zones you can have. All that also depends on how big the zones are. So there's quite a lot of things at play that basically limit how many zones you can have and how big the map can be, and obviously the big, which is in itself related to the LFAU value. So bigger map, smaller LFAU, but you can't just have a massive map. You can't just have one, 200 gigabyte map or something. It would just be too big for memory, but the numbers don't work. It's always a power of 2, which is many things in Filecore are always powers of 2, and the fact they're stored internally often as basically the log2 of the value. So sector size is stored as log2 sector size. So it's like 9 or 512 bytes. Basically means you can feed that into a shift to get the value you want, and they can store them in bytes. That you can store a lot more things in one byte if it's a 2 to the log2 rather than the actual value. So that's kind of where the LFAU comes from. I spent many a frustrating moment looking at code trying to work out how to generate it. We can come back to that. The dollar is the root of all directories. I think that was a quote I saw on a FidoNet post something once. So the root directory is usually stored after the map. After the maps, because there are 2 copies of the map. They're always written together, so not quite as useful as you might want. But I guess if one gets corrupted, disk corruption, you can use the other one. I think ROCC only ever uses the first one. The second one's there, so things like DiskNight can read it. As we kind of said earlier, up until ROCC 4 time, or 3.8, but that was the internal release. you're limited to 77 entries of 10 character file names, or directory names. So why 77? Well, you have to work out the maths. Each directory was 2 kilobytes in size. And if you have 77 times 10 bytes for the file name, 4 bytes for the load offset, load and exec addresses, which basically was a file type and date stamp. The length, so that's they're all 4 bytes. You got 3 bytes for the internal address, which is the fragment address, plus an offset into the fragment, plus 1 byte for the attributes. Whether it's accessible by readable, writable, locked, all that stuff. If you add all that up, it's about 2,000 bytes. By the time you add the varying headers, checksums, and the bits, gets you to the 2K basically. So that's why it was always 77. 77 entries, 10 bytes, 10 byte names, 10 character names effectively. And that was the case all the way up until kind of RISC-OS 4 was the first public release of that. The newer version, which had the newer directories, which could be bigger and have much longer file names. Obviously, if you have big file names, you have to be careful how you store them. If you can up the limit to 20, but then you just a lot of wasted space potentially. And it's still only 20. What if you have a 50 character file name and so on? So they actually opted for the names are stored separate from the rest of the data. So got a nice picture of that. So yeah, the old previously you'd have 10 characters, the name and the load address and the exec address and the lengths and all the other stuff. With the sort of E+ format, you would have the load address, the exec address, the lengths and all that as usual. But instead of a file name, you really just have an offset into the heap where all the file names are just stored as one list, which means you can kind of cope with quite a variation in length. You're not wasting 200 bytes to store pling run because you want to store some stupid long name elsewhere. So that's how that was done. So obviously, there's the pling boot is at offset 0. It's the start. Pling run is at offset 6 because you've got pling boot. You've got some sort of end of file name marker, and then pling run start address 6. Kind of an underscore to highlight the end. And also previously there, so you have pling boot and then 5 spaces of it. There'll actually be an end marker and then 4 spaces or 4 things you don't care about. Pling run, you've got 6 things you don't care about. Well, you need to care about 1 because it's the end of entry marker. So that was kind of how I did that. The other sort of big difference is that directories can expand. They never get fragmented. So if it expands and it needs to fragment, it'll just move. But yeah, so that basically means they can be much bigger. I don't know what the limits are on the E+ directories. They're big enough, I think, is kind of the kind of wisdom. So the fact that the directories can get bigger, is one of the reasons why the root directory may not be immediately after the map, because if it has to be moved, it will no longer be there. And the address of the root directory is stored in the disk record, amongst other stuff. It's one of those cases of it'll be after the map, but you can't rely on it being after the map. So always use the disk record. I think in practice, almost always is going to be after the maps, but don't rely on that. That's where you come undone. So I guess going back a little bit to sort of other things we know about Filecore is I think everybody who's kind of used it for a while, the limits on disk sizes. So up to 3.5, which used byte addressing. So when you wanted to refer to something on the disk, you gave it an actual byte address. So that kind of gave us the 512 megabyte limit, which because there were 32 bits in a word, 3 bits we used the drive. The drives were 0 to 7, and that gave 28 bits left for the address. So 2 to 28 is that number, which is 512 megabytes, which was the limit on everything up until the RISC PC, including the RISC PC, the first RISC PC. In RISC-OS 3.6 came about. Sector addressing. So now instead of saying I want this byte, you can say I want this sector. So that now gives you a bigger range. You can get more addresses for your 26 bits because sectors are generally 512 bytes. That gives you that number, which is 256 gigabytes, which is the other limit that everyone knows about, which is the biggest you can get a RISC-OS disk on a on a 512 byte sectors. Most things like 240 anyway. And then I said 5.28. It might have been earlier because I think it was a titanium with 4K sectors. You have 29 bits still, but each bit will get you a sector of 4K. So you have the 2 terabyte limit, which I think is as much as you're ever going to get realistically on a Filecore disk. So yeah, that's where those numbers come from. Yeah, I guess the one most people know about currently is the 256 gig for any Filecore formatted media. Probably one that hits most people. If you've got a big memory card or something, possible to go over that. So it's formatted the first bit or something. So yeah, some sort of final Filecore thoughts, I guess. It's been this RISC-OS format since 87-ish. And it obviously goes back, predates that by a fair bit with its sort of legacy of Arthur and before that the BBC. It's obviously, as you would imagine, it's all handwritten ARM assembler, which makes further changes far more tricky. It's obviously had a long history. It's not the nicest of code to deal with. It has the ingrained limit of four floppy drives, 4 hard drives, which gives you eight drives per filing system. Some filing systems tend to work around that with the what they view the floppy drive and the hard drives a little bit fluid. Certainly some of the SCSI cards I remember on the A5000 era stuff just treated all of them as hard drives or something, so you could have 8 hard drives or 8 partitions or whatever it did. And they are mostly static. There are workarounds, I guess, to handle removable devices, but they are kind of workarounds. Normally, they just assume the drive is there. So if you've got the way you handle plug-in USB sticks, it's SCSI FS goes, yeah, I've got 8 drives. And as you plug them in, it allocates, picks the next drive off, and you can use that. But actually, the drives are always there, and they just, they're like changing the disks, I guess. I guess the biggest kind of issue causes a lot of problems is that it always assumes that it's going to use the entire disk. There's no real partition support. There's a little bit to support RISC-X, but I imagine the number of users of that can be count on the fingers of half a hand. And a lot of what it does is kind of based on the needs of what I call spinning rust. It was all designed around hard drives that spin or floppy drives that spin. Drives that spin and move heads around and read and write data that way. A lot of that isn't really applicable now. Having the map in the middle is great for being able to access it quickly. if you've got an SSD, it doesn't really matter where it is. I think it's like that. So it's all kind of based on those needs. And the way that it works is that you have a module that provides you sort of access to the hardware. So the ADFS module will give you access to the well, it's SATA now, isn't it? But initially, on the early Archimedes, it would have been the ST506 drives, and then when they introduced the A5000, the IDE drives, and the varying floppy drives. But then the only way you can ever access data on those drives would be via Filecore. So it was kind of doing two things. It was kind of the file system layout, but also how you talk to hard drives. So it was a little bit of a mix, of stuff. Yeah, so that's kind of where we are. I believe it's kind of been quoted in several places that it's probably out of things that can be easily done to expand what you can store on a Filecore disk now. I believe having a longer ID, you can kind of push it a bit, but ultimately it's kind of doing anything drastic is going to be a major change to it. In fact, the thing I've not actually put on there is the way the map works. The way the map is so tied to the size of the disk and the size of the disk changing the size of the map, and then the map change where everything is one of the reasons it's very hard to write anything that can be used to resize Filecore disk. So this is why why you need something like system disk to kind of change the size of it. It's very tricky to do, because if you change the size of the disk, that changes the size of the map, that changes where everything is, and then initially the first thing that happens is if you change the size of the disk, the map moves. So if you now need to move your map, well, something's probably going to be where the map now needs to go to, so you've got to move that, and it's such a convoluted, complicated thing to do that it's the effort to do it is probably more than anyone's going to put in. If you need to change the size of it, copy the data off, reformat it, copy it back again. I believe not just the maps in the middle, but it places files going out from the map as well. So your initial files are towards the middle of the disk, and as you fill it up, it fills out from the middle, not in from the top. Which means if you want to shrink something, you have to move everything. So it's quite the location of the map is clever, but causes other things to be somewhat more. So yeah, that's kind of a quick history of Filecore and a bit of information on how it works. I'm going to just pause at this point to say, is anybody any questions?
Yeah, whenever I look at PC disks, they're always looking at defragmenting. You don't ever seem to need to do that on RISC-OS. Is that the way the Filecore is written, or is it just a very bad on the PC world?
I think well, it is. It doesn't really need to defragment as much. I guess partly the files are generally a lot smaller as well, and they probably don't move around as much. I think Filecore will or can move things around within a zone, so it can make better. It can defragment itself a little bit, but generally, I think the reason you need to do the defragmentation on sort of PC systems is, I think, to do the way it accesses the fragments. Was I think on RISC-OS, it's not as, you probably wouldn't gain as much by doing it, which probably no one bothers. So there is that.
Yeah, I suppose initially PCs use a hard drive rather than RAM, or as well as RAM. Whereas I don't think RISC-OS does. It just uses RAM generally, doesn't it?
It uses RAM a lot, and I think people, RISC-OS doesn't tend to create as much in the way of random files around that the PCs do, Windows does, or DOS does. So I think once you put something on, it kind of stays there. You might move it around, but well, you move something in a directory, it doesn't move the stuff on the disk, right? It just stays there. So I imagine it's a combination of those that I know. Reading somewhere now that actually not needed to defragment was a key sort of design that they in Filecore, rather than having a system where you've got to defragment your drive every now and then. Yeah, so I think it's the way it handles the fragments. I say part of the use is probably different enough that it just doesn't become an issue. I think you can get DiskNight to tell you how many files are fragmented. And of that, often it's these many have to be fragmented, because if they're that big, that's you have to do it. So, but most files are fairly small compared to a zone. So.
It's interesting you were saying that it only allows, was it 8 disks as such, whereas I think PC, Mac and Linux allow A through to Z, don't they?
Yeah, I mean, I think, PC give you 26.
Yeah. That's a fair few.
Yeah, Linux is just however many you can plug in.
Right.
But yeah, I think, again, probably 4 floppy drives will seem to be a reasonable upper limit. And I think, most people would have had 1 or 2. They needed to have a number.
Yeah.
8 seems reasonable. I think it was 8 on the BBC as well. But because they've used 8 bits, 3 bits to give you those 8, you only get 29 for the address, which gives you the other limits.
Yeah.
Yeah, I think a lot of things about Filecore you can kind of think, well, it's a bit of a limit, but you have to kind of think when it was made, and I presume when it was initially designed, 512 megabytes was an enormous amount of space. You're never going to use that.
Yeah, it's like you were saying about MFM drives. I've got an old A40 421. I think I've got SCSI and the MFM's died, but it was 20 meg, and we thought, how are we ever going to fill that? And
how are you going to fill that?
You put a big WAV file in something now. Oh, we've gone past that. Yeah,
it's filled it. Yeah, I remember
never mind the video.
When I was at school, we had a network server, one of the SJ ones it was, but it had a 20 megabyte hard drive for everyone.
What happens with other filing systems, such as Net filing system or Landman filing system? I thought they still had to work through Filecore. Is that not what they do?
Things like NetFS or Landman will go through file switch, which is the sort of the higher level again. Filecore kind of provides you with the disk access thing, so you can, if you're providing a Filecore filing system, everything goes through Filecore, and Filecore basically asks you to read these bytes and write these bytes and that sort of stuff. So all the file opening, file closing, looking for files, directory searching is all done for you. Things like Landman. NetFS a bit old now. Things like Landman, you're kind of a higher level or lower level, as your point of view. That when you want to see what's on a Landman share, you would have to ask Landman, the Landman file system, list me the files, list me what's in this directory. If it's Filecore file system, that's all handled for you by Filecore, and basically all you've got to do, it's not that easy, is to feed Filecore some data or just store some data it's given you, which is why those other file systems didn't have the limits that Filecore do, especially with the 10-character file names. There were a few things back in the day, weren't there, that were long files, and there was something else that would kind of work around that. So they were non-Filecore file systems.
Okay, thank you.
Or for any more, I could actually. So yeah, one of the things I did do was some code, sort of some Python to sort of do disk formatting, which was the way you have to format them is, can be quite fun. Let me see if I can share that. Stop sharing on that one. Share again. Yeah, it's now shared by text window, but everything's away. What? Whatever. Windows Defender is getting upset. Yeah, so one of the things you have to do when you're kind of formatting, as it were, any sort of modern disk like an SSD, it doesn't really have a number of cylinders, heads, things like that. So one of the things I kind of did there was this kind of a little bit of code that basically says just try and find a shape that fits, and all you're trying to do is find some values that will give you the right number of overall sectors. Yeah, internally it all uses logical block addressing, but yeah, there are still times where it kind of it works in this spinning rust model, as I called it. So yeah, when you're trying to format it, it's like I just want to find something that fits. I think every time I run this, it kind of really weird shapes, but ultimately it doesn't matter. It's just a way of accessing the blocks. And then you have to do this kind of thing to find the allocation size, which is you just keep trying it till it fits, basically. Which is how H1 works. Actually, yeah, the code is a bit of basic there in comments, which I commented. Yeah, so H1 works in the same way. It basically just tries to do a small LFAU and just keeps adding to it. It picks a small one. That doesn't work because of these things. Tries the next one, and so on. Are there any other questions on Filecore? Any corrections? Because it could well be, yeah.
Sorry.
Not a question, but just a comment about the 4+4 on the filing systems. I think Acorn kind of envisaged that they were just creating ADFS for floppies and hard drives. So they were thinking very much of the capabilities of an A310 or whatever, where having 4 hard drives on the ST502 bus was probably the hardware limit, and 4 floppies, as Chris said, was irrelevant, or was more than anybody was likely to have. And their expectation was that you would use other filing systems to expand beyond the 4, rather than sort of inherent to Filecore to provide all those filing systems, so all those drive icons. So, they had RAM first, they had ADFS first. Later on, there was SCSI first and an IDE first. Well, that was third party, but the idea was that you would have multiple filing systems, each with their own 4+4 drives, and thus the Filecore limitations was not intended to be a major problem back then. It's only now when almost everything is either SATA or NVMe that you start, and you want to have lots of partitions, that it starts to become more of a sort of legacy craft.
Yeah, in fact, Filecore came about if you look back to the module history of things, it came about in RISC-OS 2. I presume it kind of was spun off what would have been ADFS in Arthur. And then, one of the things that came about at the same time would have been RAMFS. That was RISC-OS 2 had that as well. And I think RAMFS is basically a big floppy. Small floppy, depends on how big a RAM disk is. It made sense because obviously all the drive handling, all the file system handling code's already there, so all the ways of opening a file, cataloging directories, all that stuff done for you. All you need to do is feed it bytes. Store bytes that it's given you, which if you're writing RAMFS, that's quite easy. You just dump them into your bit of memory. So yeah, I can see. Like Andrew was saying initially, that would have been designed around the sort of ADFS, which would have dealt with ST506 drives and floppy drives. And it kind of, that would have been what ADFS did. So that's what Filecore did, and then propagated on from there. I think Acorn's IDE was done via ADFS, wasn't it? But third-party ones had IDEFS or something like that. So, like over 2 years ago now. Gone. I will continue on slightly caught at the time with BlockDevices, which was the second half of my my presentation, which I sort of tried a new way to do disks. It's not quite as long, this section. Let's just close this because I've lost my speaker notes. So BlockDevices. So it's I guess ultimately, simply, it's a series of blocks of a given size. You might find a hard drive, or more likely these days a SSD, based on the similar concepts in Unix and probably others, to be fair. But if you use any sort of Linux system, it's /dev. I say SD, but that's pretty old now, isn't it? NVMe something or other. It's just a bunch of blocks. Although in Linux you can access them in bytes. The kind of idea is that the BlockDevices module itself is really just an interface. It doesn't really provide anything. And it's the driver modules that actually do the work. So yeah, you can always call through BlockDevices and it will pass that on to the appropriate driver. And kind of they can be stacked. So you can have a block device that's based on top of another block device. Just kind of go onto that a little bit in a moment. And dynamic changes are sort of built in, so devices can just turn up and go away. Much more in line with how, not NVMe, but USB sticks and things like that. Just if you plug them in, they appear. You unplug them, they go away again. And certainly from the outset, we have support for 64-bit block addresses. This gives you huge devices. It's actually your blocks and sectors are kind of the same thing. I kind of use the word blocks. That's what NVMe calls them, actually, because they're a sector is a part of a disk. It's in the name. But obviously, if you're just based on NAND chips or something, then yeah, it's just another bit of the chip. So it's not really a sector of anything. So the interface is basically read me some data and write some data. Yeah, slightly more than that. There are a bunch of other things, which are a bit like the MISCOP calls for anybody who's done anything with Filecore type devices. Yeah, they try to be as generic as you can. Not every driver will provide all of them, or even any of them. But the ones that it does provide, they try to be as generic as you can be. It's actually quite tricky to do because even things you think would be generic aren't, between different things. But the idea is that where it can be as generic as possible. So the idea of them be you can target any device, doesn't matter how it's provided, and it will work. In terms of providing file storage, then it's really just read and write that you need anyway. Already verify as well, which is in there, but nothing provides at the moment. So yeah, there are kind of two things. You're either writing or reading data, or you're doing some sort of operation. The other operations are somewhat more varied. But yeah, the kind of the concepts there. So there's the hardware drivers, and they are what's used to actually do the work. So the current focus driver is the NVMe one, the fastest NVMe driver in the West, essentially. It's very quick, but its job is really just to provide data or to store data, and that's all it really deals with. The block device will basically say to it, here's some data, I want you to write it, I want you to read this data into this address. Everything's done as blocks. So if you want half a block, you've got to read the entire thing into a buffer and read the bit you want out of the buffer. If you want to write half a block, you've got to read what's there, update it, and write it back again. That just makes the whole thing simpler than trying to handle byte offsets into blocks. Yeah, it's not easy. Most things tend to work at a block level anyway. So, like everything else on BlockDevices, these can come and go at runtime. Obviously, for NVMe drives, it's not likely to change when the machine's on. If you pull your NVMe drive out when the machine's running, you've probably got bigger problems than updating an icon. But yeah, other things, if you plug in cards, memory sticks, things like that, yeah, that's more likely to need that. When the driver module rather will sort of sit and do whatever it needs to do to detect that. When it detects the drive it's going to handle, it will kind of just register at the BlockDevices. There's no limit, you can just keep registering them. Well, there is a limit. I think it's whatever 32 bits worth of devices are, but it's not likely to run out. Yeah, so the NVMe driver will announce all the NVMe drives it finds. Current hardware, that's going to be 1 or 0, but the concept's there. So if you had a SATA driver, the SATA card can have many chips on it. SATA chip can have many drives attached to it. Theory, you can have several NVMe drives in the same machine with a suitable PCI setup. I don't think anything does that yet. I'm pretty sure the code doesn't handle it, but it can. The concept's there. You just create as many as you want. So yeah, currently NVMe is the focus, which works pretty well. SATA would be, I think, a useful target. I don't think would be too involved. There's kind of there's a SATA driver module now. If I sit on top of that, if you were mad, you could do on floppy disk. Nothing's stopping you. Probably not really very useful use of anyone's time, but yeah, you could do that. Speaking of floppy disks, I did see on YouTube of all places, stuff on there. There was someone had made a floppy disk RAID system of like 30 floppy disks. Yeah, just because you can doesn't mean you should. So yeah, that's the hardware drivers. All those modules are concerned with is talking to the hardware and providing bytes, saving bytes, and they will then also implement the MISCOPs that they care about supporting. Obviously, they're going to just vary quite a lot between what your driver is. If you have you can have a driver for a RAM disk, which doesn't talk to any hardware, but shuffles bytes around. If you have a driver for a NVMe drive, you've got a bunch of things that can do. A SATA be a different bunch of things. Some overlap, but maybe not a lot. So that's the hardware level. So that's kind of the basic talking to the hardware level. That gives you access to the device and a way of putting data to it, getting data from it, nothing else. So partitions, everyone's favorite thing, potentially. Been kind of on the things we'd like to do for a long time. But it's kind of idea that drivers don't necessarily talk to hardware, they can just use other devices. This idea is basically used to provide a GPT partition support. I could have done MBR, but MBR is a bit rubbish now. So I might as well use GPT from the start. But they're trying to find information about GPT is a bit confusing now because there's a chat thing called Chat GPT, isn't there? No, I want the partition system. Yeah, using it to provide partition support. You could also use it for RAID. Fairly, that would be a RAID driver would talk to a number of hardware drivers. So when you save a byte, it would save it everywhere. Save a block, rather, it save it everywhere. Due to the way the whole thing is quite dynamic, when a device is added, that's kind of RISC-OS terms service call goes out to say, hey, a new device is here. The GPT module will go, oh, that's interesting. We'll then try to read a GPT table. If there is one, it then creates a new device for each of the partitions in that table. And then when someone call comes into a partition to say, I want to read block 10, the GPT module goes, oh, actually, I know that device is actually the partition that starts at block 5000, so I'll read block 5010 and feed that back. And all this happens, we're still nowhere near Filecore, so there are no limits. Well, there is a limit. It's whatever 32 bits worth of blocks gives you, but yeah, not a limit I'm going to worry about. Which does mean that we get on to the next bit, I guess, which is putting a Filecore system on it. You can actually have the Filecore system anywhere on the disk, because as far as Filecore is concerned, it starts at block 0, because that's then mapped before Filecore is even aware of it. Which is what NVMe FS does. So that provides a Filecore interface to the BlockDevices. Much like any sort of Filecore filing system, it uses Filecore to do the filing system bit, and it provides what the Filecore is the hardware, which is the block device. Yeah, the thing is called NVMe-FS. In theory, you could have 8 terabytes of data on it if you had 4 2 terabyte partitions, which is the maximum you can have. There's nothing special about it has to be NVMe, except it's very confusing if your NVMe-FS module spoke to your RAM disk. So, but in terms of talking to block devices, it's all just the same. So while the block devices themselves obviously aren't constrained by Filecore, NVMe-FS is a Filecore filing system, so they are. Yeah, that's why you have your 8 drive limit. Although NVMe only uses hard drives, so yeah, that's where you have four partitions of 2 terabytes on an 8 terabyte drive comes from. I guess you could use 2 of them if you use the floppy drive numbers as well, but I'm not sure what you do with 16 terabytes. I know we're doing 8 terabytes on RISC-OS, but then 16. They can be anywhere on the disk, like I said before, so there's no reason they need to be at the front of the disk, as they would be if you were accessing the hardware through a Filecore filing system. And yeah, the partition type I can see that's going to be important to tell Filecore drives from everything else. At the moment, NVMe-FS just kind of goes out. I will talk to any drive and stick an icon on for it. But if you start having like Linux partitions, then you don't really want an icon for those because it's not going to work. You click on it, it'll just go, this drive's not formatted. Much like MBR, but the GPT partitions have the type. So NVMe can, if you build it with such an option, just watch for certain types and then ignore. We won't bother to pick up icons for non-Filecore partitions. It actually works internally a bit like SCSI FS and the like. It pretends it's got 4 hard drives. There's a flag or something which you set to say it's not really there, which means the icon's not on the icon bar. When it detects a block device appearing, it will then go, oh, okay, well, I've got a spare drive. I will allocate your new device, your new block device, to be drive 4, and the second one drive 5, and so on. When they unregister, the opposite happens, unmaps them. Much like if you unplug your memory stick. Yeah, so it does support that. but yeah, the partition type is going to be more useful if you start having different partitions. It's also got a slight kind of clever bit where, because a fairly common case on any sort of RISC-OS system is there aren't any partitions, we just use the entire disk as Filecore. That'll handle that. But if you have the whole disk mapped as what's going to be drive 4, and then it gets a notification, so a partition's appeared on that drive, it will unmap the whole disk. So you don't end up with an extra drive that's not going to be any use to you. It's kind of a slight, workaround, I guess, for that case where you need to be able to support no partitions and a system with partitions. But obviously we can use other filing systems in theory. Not that I've done any of these yet, but things like FAT32FS or ISCA-FS, which is the X3 reader. Although I think that's all in assembler, which is, rather puts me off doing anything with that one. So there's, they can all be done without going through Filecore, which means you could, in theory, I don't know if FAT32FS would support it, have a bigger, a big fat partition, even with 512 byte sectors, than you can with going through Filecore, because you don't have that limit. I think FAT32FS is built on some library, but I don't know what that restriction is. If anybody had the time, inclination, money, whatever, ultimately, you could probably port something else, X234, whatever it is up to these days, XFS, I don't know. Some of these are really not going to be that suitable for RISC-OS, but there are no doubt other filing systems that could be ported, that you could then use. You'd like to think that, something in C you could pick up off some sort of BSD-based tree. The block device interface isn't going to be the same as it expects, because normally it works through a file, but ultimately your code is going to be reading and writing bytes or blocks or something. I think the issue with a lot of these filing systems is going to be how suitable they are to RISC-OS, which is probably someone else's call. Well, I do now have a slight demo. This is always scary. Live demos. What could possibly go wrong? Literally every time I do a live demo, something does in fact go wrong. We shall try. Are there any block drivers questions? I guess it's a slight whistle-stop tour, because we have something to show, which is always more exciting if it works. So this is a CM4 based machine. I'm going to share. There we go. So here we go. It's my development CM4 machine, which sat on my desk. Although I have to talk through it via a PC so I can share the screen. Can you see the screen? Has it shared it? Yeah, we got thumbs up. That's good.
It's showing the whole of your PC desktop, Chris.
Oh, that's not so good, is it? I'll do that. Half what I want. Stop share. Let's try again. See, technology. It's just, that's what I want. Not one. What actually? All right, let's try again. Is that more like it?
Looking good.
Looking good. So yeah, this is my otherwise you get kind of meta thing you see yourselves and stuff. So yeah, this is my CM4 based development machine. So it does have have 2 NVMe drives on it. This one is about 600 gigabytes. This one like 200 gigabytes. So yeah, these are 2 partitions. They're not very exciting because they're both empty. Because of my development machine, I don't tend to store anything on it because I end up trashing it with irregular. Well, let's just try this out. And, So just the modules. We've got the BlockDevices module here, which kind of provides the skeleton, as it were. The BlockDevice, BlockDev part GPU. Yeah, there's a limit on my module names, a little bit shortened here. So that's the GPU partition module. That's the NVMe driver, and they've got NVMe FS, which actually provides the filing system. So you get a list of the devices. So the entire disk, SD card, it's not a disk, is it? Is this one, which is, yeah, it's about a terabyte, isn't it? And I've split it into 2 partitions. Yeah, with, so actually that one's not really going to work. So no, it probably does work. It's probably a 4K, pretty a 4K device. Obviously, with the 4K, you can have bigger drives. You get it's the 2 terabytes the limit. So that's kind of what size of it. That's what's going on. NVMe FS actually has a new command. Newish. It basically tells you what NVMe drives map to what lock devices. More for working out what's going on than anything. But as we kind of touched on earlier, there are these other operations that we can now do, and thanks to Andrew, we can actually show one of those in use. And this is the smart stats for my hard drive on my NVMe drive. So these are basically what you get out of the NVMe. It's a fairly standard. It is totally standard, actually. Block of data. Some of them are, more useful than others, I guess. I think not everything's guaranteed to be there, but it's always the same format of data. Yeah, the temperatures are all in Kelvin. First time I saw that, I was like, I read the data. That can't be right. The drive can't be that hot. I read it was Kelvin. But yeah, that's what it does. Obviously, you can find all this out. I just copy something to the drive. It should update the stats, apparently. Yeah, I know. Bollocks. I tried to copy everything at once, haven't I? Do that. Never mind. Yeah. So I think these are. I think the data written is in. It's in some quite big numbers because obviously it's. But I think it's stored as like a 128-bit number, so it's a bit of processing to get it to a valid thing you can show. Yeah, so it tells you sort of the power on time. I think this is how much space it's got to remap. So you can kind of use that to detect all the drives wearing out because it's going to be using up all its remappable space. And these are quite, I imagine, be useful to kind of tell you if the thing's got too hot and for how long. So if you start getting entries in there, probably need to be looked at. I think unsafe shutdowns is oddly high because I think all shutdowns are unsafe at the moment. I think that's when you don't. So it's safe in the sense that you've written all the data, but if you don't shut the device down fully in the expected way, which often happens if you crash your driver. As a development machine, that does tend to happen. So yeah, that's all done with the new MISCOP calls, which I can. It's got a little bit of. Find which one I want. That one. A bit of code. So that's the sort of the basic that kind of goes behind it, I guess. Andrew's very kindly put a nice fancy GUI on it, so you don't have to run this and just get a bit of text that says the same thing. So yeah, you call it device op. These calls are kind of to get the models, serial, firmware, this stuff. and then you call another one, which is this one, that one, which reads the smart information. Yeah, basically that's what you get back out of it. It's it's all defined in the NVMe spec basically. Fortunately, it doesn't really map onto the IDE one. There's not a lot of common honesty. Well, there is, but they're done in such different ways. So the idea of those sort of miscop calls is you can just kind of add things that you might want to do. It's a little bit hard to define exactly what you can do with them because it is very dependent on the device. But yeah, there's some examples of some in the header file. There we go. Most of them aren't actually implemented, admittedly, but so yeah, there's these ones. So the well, in theory, trim would be a good one to have with these sort of solid state devices. Probably not too hard to implement it, at least in terms of sending it the right commands. Yeah, that's quite how to get Filecore to do anything with that. I'm not sure. It's been offline operation or something like that. One of the other things you can do, which I'm not going to do because it'll trash my drive if I run it, is you can change the block size. Most NVMe drives let you change the block size. Leave this one. Yeah, I can cancel out this one. So it's so it takes you the text that you can do 2 block size, you can do 512 bytes, which is good, or 4K, which is better. The good, better, best, whatever the definitions are, again in the NVMe spec. But I'm not going to run this because it'll then go ahead and change the block size and trash all my data. Nothing on there, I suppose, but that again is done through the miscops, so you've not got to do any. It's tried to abstract the idea that a device can have different block sizes. It doesn't really matter what that device is. Currently, NVMe does it. You could, in theory, have a RAM disk that does it. Things like that. But yeah, it's trying to end up with a suitable thing. There is this thing here, which is the enumerate calls. So obviously you get a tree. It's kind of a tree structure. So all the devices are 1, 2, and 3. Top level device is 1, just because it's the first one that's added. And you can then say, okay, well, this device, what are the children? In this case, are the partitions. Yeah, so that's the ideas behind block devices. It's really just a kind of a new abstraction of talking to devices as blocks rather than bits of Filecore calls and things like that. So yeah, are there any questions or comments on that one? Andrew might have some. I don't know. I'm impressed this program works straight away. First time out the archive as well.
That's a relief. Would it make sense to do a version of the RAM disk with block drive devices support?
Yeah. I think I sort of had a go at it, sort of during debugging because it was a good one. It's a good one to test with. It doesn't trash anything. I guess you just shove in a dynamic area or something like that. In what would be interesting, or some definition of such, would be a sort of a RAM disk that had sparse allocation or something like that. Resizable, block. I guess you could resize it, but then you're back with the Filecore issue of resizing a Filecore disk can't work. But yeah, there's no reason why you can't make a block device RAM disk. Just be a dynamic error, something like that. Certainly, it'd be useful for testing stuff out or trying different file systems. I guess that would, a way of doing something that you can throw away at the end is always useful if you're trying to experiment with anything. I imagine SATA would be a useful one to do as well. That does, in theory, allow you to have RAID as well. It's a bit further down the line how you'd handle that.
Is there a website that you want to plug for?
The code is all on GitHub. I'll have to post a link. I can do that. Stop sharing that for a second. I can't easily do it on. It's in a bit of a state of flux still. I've kind of managed to lock it down quite a bit of recent times. Can you send a message? Oh, I put it in the chat, can't I? There we go. That's what the chat's for. That's the BlockDevices link. There's actually an initial implementation of a RAM disk there as well. So yeah, I think it just created a dynamic area to dump the data in. So yeah, that's
cool.
It's I think it's probably got quite a few useful things that can be done with it, but it's yeah, it's just getting a bit of use on it. Certainly, it's having been able to use proper GPT partitions. It's been a big advantage. Rather than, I think the problem is with doing it with Filecore is you can't easily use GPT because it kind of needs a bit of space that the disk record's in. And if you then save a disk record, it's going to splat the partition table, which is a bit useless. And was never designed for such a thing, I guess. That's, Filecore was always ever designed to use the entire disk, which is what it does. So trying to add partitions into that is not an easy thing. It's why doing the partitions outside of Filecore just means that if Filecore can say it's just another disk. Excuse me. Yeah, so that's sort of a bit of information about BlockDevices as well. Yeah, it's working fairly well. What's the next project? Oh, God knows. I've got enough spinning plates as it is. Yeah, could do with finishing off this three. It's probably Python needs an update as well, doesn't it? It's new Python out now. Really ought to update to it. I kind of want to do the new one because it's 3.14 and that's Pi. Yeah, of all the reasons to do it, that's probably not the best one, but it'll do. The next project we win the lottery, and then I'd have much more time.
How practical is it to sort of veneer from BlockDevices to other pre-existing filing systems, like sort of the USB system uses SCSI? Would you need to re-implement SCSI for BlockDevices, or could a module to interface?
In terms of the Filecore bit, you basically take what's currently the BlockDevices NVMe FS and copy it and change the name and change the one of the bits of information in the BlockDevice header is the type. Basically, it's it's an NVMe device or it's a SATA device or something. You kind of use that to filter out what devices your particular FS wants to respond to, and then it's almost a clone of it's currently NVMe FS. in theory, you could have like a general block device FS, but then you run into the Filecore limits of can only ever have 8 drives. And also, I think, rightly or wrongly, the way RISC-OS works is each different type has its own filing system. I think if you go too far away from that, is that going to be too confusing? I don't know. But certainly in terms of the main issue with Filecore will be the drive limits. In fact, only have 8 drives. So you can't easily just, if you had one filing system, that would be 8 drives for everything, which is not going to be enough. So the only thing that would, I think when I was trying out the RAMFS, for RAM block device, I just took NVMe-FS and took the disabled the check for the type, and then it just responds to any block device, and I could just use my RAM disk as if it was an NVMe drive. So yeah, the short answer to that is it's probably almost trivial just to roll another FS to talk to. If you provided a SCSI, USB type thing, you could provide another FS to sit on top of that. And give you your next set of 8 icons, basically. This is what you get for each FS is another batch of icons. Obviously,
Chris, speed-wise, is there some eking out of extra speed that you could still do with you sort of limiting the speed while you get some confidence in the drivers?
I think speed-wise, the NVMe driver is pretty quick. My limited testing of it, I think Andrew's probably used it more than I have. Most of what BlockDevices does is fairly light in terms of speed, knock-on speed effects. The partition module does a bit. It does a bit of sums, but you're effectively adding a number, adding an int to another int, 64-bit ints, but it's not. In terms of compute time, it's not really much. So I think it's fairly within the confines of what RISC-OS can do. It's fairly quick. One of my sort of slight worries about RAID would be if you're writing to 2 disks, which you would be doing. Do you have to then, it would then take double the time potentially. You could possibly do some things in parallel, but we're not great at doing that in RISC-OS land because it's all designed around single processor with single threading. So yeah, I think you could do something with writing to 2 SATA drives if you could get. You'd have to do something with background operations, I think, to basically tell each controller, here's the data, write it. They've both said they're done, complete, but they should be able to do it at the same time.
I think the biggest performance issue right now is the speed that is imposed by Filecore itself, because the NVMe driver will approach the same speed as RAM disk, and at that point, if it's as fast as writing to memory or reading from memory, then it's hard to imagine within the confines of a Filecore filing system going a great deal faster than RAM disk. What does make a difference is using 4K sectors versus 256. It's more efficient to use 4K sectors. And so you do actually see the 4K NVMe driver outperforming RAM disk under certain circumstances anyway, when using the 4K sectors. I think RAM disk still has the lead in certain situations, but you can actually exceed it with 4K sectors. So at that point, it's hard to imagine the system going a great deal faster if you can't actually read and write to memory with the limitations of a Filecore filing system.
And some of that is going to be what Filecore's doing internally, and changing that, upgrading that is a big challenge because it's all in assembler. just, why it would be nice to. I mean, I suppose if someone said, "What would be the next project?" It would be to probably find some other FS to port to it. At least an example. I think DOSFS would probably be easy. Not DOS, FAT32FS would probably be fairly easy to do. It's finding something with the right, the right interface, basically.
In fact, at the moment, FAT32FS does work with because it actually just calls the NVMe filing system, so you can do up to 256 gig.
Yeah,
but
it'd be nice.
Nice
It'd be nice to. I always feel it's like you're calling NVMe AFS to read the sectors. It's like, well, you could bypass all of that if you if you get it to talk straight to BlockDevices and just. I don't think it'd be much quicker, particularly because I imagine a disk op call isn't going to be particularly expensive in Filecore terms. I think the slowdown in Filecore is its processing. So it's limiting on the speed of writing files because of what it's doing with the map and the directory and all its other checks and stuff that it does. Whereas I think a disk op is basically it just saying, "Get me these sectors."
Yeah.
But being able to bypass Filecore would get around that 256 gig limit for 512K sectors anyway.
Yeah.
Any further questions for Chris? A big silence.
Everyone's fallen asleep after it.
They're all awake anyway.
Well, another question from me. I suppose I should be doing these via email, but what's needed in terms of getting from where we are now to a fully ROMable version of BlockDevices?
Probably not much. I think what's kind of been the sort of hold up is, of course, once you kind of commit to a version, it's a bit set in stone and then very hard to change things. But I think we're probably at the point where, setting in stones probably just needs to happen. I mean, if we need to change it later, so be it. Believe everything should be ROMable.
Sorry, I didn't mean to put you on the spot like that.
Yeah, no, I mean, I've never tried building it for ROM because of the overhead of building for ROM. But there would be no. I think the design and the theory of BlockDevices is you can load the modules in any order. You can re-init them in any order. Doesn't really matter. It all works out. Though I have seen cases where loading certain modules in a certain order works and another order doesn't. So there may be a bit of investigation to flush out that. I think I figured out what it was. Need to fix it. I think the modules should all be easily runnable from ROM. The driver potentially. That should be okay. I know at one point we kind of had a bit of a delay in for something, but I think it should be okay because the driver that talks to actual hardware will just start up, set a callback, do its thing. So the only thing I'm thinking of is it going to be a case where the machine would boot up, but the filing system wouldn't be ready at the point that it tried to boot off it. You're thinking of it booting off the NVMe device, basically.
Yeah. I mean, on a Pinebook Pro, it's not really relevant anyway because the hardware itself won't boot off off NVMe directly, only off eMMC or SDFS. So you're always going to have a step in there, so it doesn't really make any difference. In theory, you could boot a Pi 4 directly, or CM4 directly in NVMe, couldn't you?
Well, I think it's not. It's almost certainly something that could be. I say my only thought would be if the OS itself gets around to trying to boot off the drive before the drive's ready, but that's probably not insurmountable. It may well be that it comes out in the wash, but other systems, other drives must have a similar concept. So my thinking is it probably just hang, wouldn't it? Just wait. I suppose the difference is that the drive isn't even there until it's announced, but you could always get NVMe-FS to kind of wait a bit for the first access or something to give time for things to settle down. I imagine it'd be a case of try it. Probably the best.
Yeah, I guess that's the Elon Musk method.
See what happens. It's the best.
Yeah.
Perhaps that's a good thing to investigate. Just try and build it into a ROM, see what happens.
Yeah.
I mean, to be honest with you, having the NVMe portion actually in ROM is, to a degree, slightly less important than having block devices. That if you've got the block devices module in ROM, then you've got the building blocks for other filing systems to plug into. And if we're going to sort of push forwards in making this sort of 64-bit compatible architecture, then having the sort of underlying core modules available to everybody in ROM would be pretty cool.
Probably more useful, isn't it? Yeah, I mean, obviously the whole thing was designed around 64-bit addressing just from the start, just because 32 bits isn't enough for addressing sectors on a hard drive anymore.
And it would be nice to bring all the sort of partition support and things to other filing systems.
Yeah, and that.
And having the core technology available in ROM might make it more of a good building block, I suppose.
Yeah, I mean, certainly implementing other filing systems through it. So it depends how well it's split between the FS, the driver bit and the rest of it. But certain things like SATA have got a driver that you could, I think, sit on top of, or just modify it because it's open source. But you could write a shim layer, I think, to sit on top of the SATA driver, and then feed into BlockDevices.
Yeah.
Because SATA doesn't change when the machine's running. That's my thought of that. It's not hot swappable. Which USB is. USB is a weird one. So it goes through SCSI FS. So.
Yeah, there's basically a whole lot of SCSI FS soft drivers.
Yes.
SCSI FS soft USBs and SCSI FS soft something else, etc.
Probably it, unless anybody else has got any.
Yes. Maybe I've got any other comments.